So friends, welcome back, and this is the third lecture in the series of charges talking about the Coulomb's law. We derived that if in case the forces F12 and F21 are taken each equal to F, and this F is proportional to Q1 and is proportional to Q2 and is proportional to 1 of R square separately, and then together with for mathematical consistency we said that F is proportional to Q1 into Q2 into 1 upon R square, and we got this in the MKs or SI system units. 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Okay, so this is the relation. Now let us analyze, let us try to understand it better with the systems approach. Remember, if I had a system where there were two variables, there was a system like this where I had variable y and x, and we could say only two variables, nothing else. This was an isolated system. So in this isolated system I said that let y be a function of x, and so x be a function of y, no problem. So taking like that, one of the simplest things that occurs is that y is proportional to x, which is also called sometimes as directly proportional to x. But I tell you that there is only one proportionality, and that is direct proportionality as it is. Okay. So y is proportional to x. Then we found that for every system like that, y is equal to kx, where k is neither a function of x nor a function of y. Okay. Does not depend upon x, does not depend upon y. And I answered this question in the beginning when I was introducing these kind of functions, that k is a function of what I said? I said the system, the defined system. Okay. And when I worked it out, then I found that k is equal to delta y upon delta x, or k is equal to dy over dx when dx, delta x tends to 0, is very small, etc. And I told you I related it with rate of change of y with respect to x. Okay. And when I plotted, then y is proportional to x, I got a curve like this, a straight line. Okay. And but if there are two systems, similar systems, y is proportional to x, where the constants are k1 and k2 respectively, which are given by the slopes of these curves, then if k1 is greater than k2, then the slope of k1 will be greater, if this one will be greater than the slope of this one, etc. So this is the basic. Now, with the help of these basics, let's try to understand the Coulomb's law in the first instance. What we did was that we took Q2 and R to be constants. Okay. And we found that F is proportional to Q1. So from this law I can see that Q2 upon R square into 1 upon 4 pi epsilon naught, which is put in the brackets here, and which I just say that let it be K1. So this is equal to K1 into Q1. So in the first instance, Coulomb takes Q1 as a variable. Okay, Q1 is a variable, and he took Q2 and R to be constants. So this whole thing within the bracket becomes a constant, which I relate and say that is equal to K1, and K1 is equal to 1 upon 4 pi epsilon naught Q2 upon R square. Okay. Now, if we plot a graph with Q1 on the x-axis in coulombs and F on the y-axis in Newton, then we find that we can get straight lines passing through the origin. Like this, I have just taken two cases. I have taken R as equal to constant, and I have just made a variation in the value of Q2 as Q2 dash and Q2 double dash. Okay, and we find that the slope in that case every time here the slope will be equal to maybe K1 dash, and here the slope is K2 dash. Okay, so Q2 dash is greater than Q2 double dash. Okay, so that this slope is more as compared to this slope. Okay, you have to plot it all by yourself, and you have to make arguments like I have done all by yourself several times, right? So this is a straight line like the mother curve. Y is proportional to x, y is equal to kx. In the second instance, I am taking f is proportional to q2. Okay. In the red ink, I have written q1 and r are constants. Okay. So f will be equal to in this case also the q2 becomes a variable. Okay. Rest are constants. So here within the bracket I will get 1 upon 4 pi epsilon naught q1 upon r square. Okay. Instead of k1 I will write here k2. Okay. And this k2 will become equal to 1 upon 4 pi epsilon naught. Instead of q2 I will write q1 upon r square. So they are very similar to each other. And I have drawn that graph with q1 in coulombs and f in newtons, and we will get the graph slopes like this. Of course, r has been taken here. In this case, I have taken I'm sorry, it's not this one, but even in that case, in the first case, I take q2 is equal to constant, and I just vary r, and there are two slopes that I have shown over here, and r double dash is greater than r dash. Okay, and similar curves I obtain for the second case also, where I have to replace q2 by q1. Okay, and here I will write q1 is equal to a constant, and here I will get 1 and 1, q1 dash, q2 dash, etc., and similar kind of curves we will obtain by here, right? So look here, you have taken one thing at a time, q1 as a variable, then q2 as a variable, and now the third thing that we take is that r is a variable, and whereas q1 and q2 they are constants. Okay, so I can write f is equal to 1 upon 4 pi epsilon naught q1 q2. This thing is now taken in bracket into 1 upon r square, and I take this whole thing as equal to kr is equal to 1 upon 4 pi epsilon naught q1 q2, right? There is no problem, we can take any symbols, ka, kha, ga, ga, cha, cha, ja, ja, anything you like, a, b, c, d, e, f, g, h, whatever, alif, ba, ta, sa, no problem. The thing is that you understand what is going on over there. So, the first instance I plot the force in newtons with respect to 1 upon r square, which is in per meter, a meter raised to the power minus 2, something which you are not able to appreciate readily. Okay. So in that case also, as I said that f is proportional to 1 upon r square. What kind of proportionality is that? That is the direct proportionality. Okay. So I will get it. graph like this. Here I am writing that the product Q1, Q2 is a constant. Or I can write Q1 is a constant, Q2 is a constant, etc. The slope will turn out to be equal to Kr, which is given as 1 upon 4 pi epsilon naught Q1, Q2, like that. But this thing we don't understand, okay, easily. So what is required is that I must have R in meters here, which we understand, the distance, and F in Newton. And in that case you can see that as the value of R increases, because of this inverse square relationship, so the value of the force will keep on falling and falling and falling fast at that. This graph is similar to the graph where y is proportional to 1 upon x. Okay, the only thing is that this falls faster than y is proportional to 1 upon x, and here I take x like that. So I repeat for you. I repeat for you. The Coulomb's law, it turns out to be something like this. Okay, 1 upon 4 pi epsilon naught, lovely value over here that we have. Epsilon naught, the permittivity. What I said? Permittivity. Like when you enter a class and you are late and you say, "May I come in, sir?" One teacher says, "Yes, yes, yes." One teacher says, "Oh, where were you?" Another teacher says, "No, no, 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 out." Okay, go and stand outside for 5 minutes and then take my permission. So permission varies. The level of permission or the degree of permission is different from different teachers, and similarly there is permittivity on who permits the medium. Okay, this is the permittivity of free space, and we obtain the value like this. Okay, please understand that they are individually proportional to Q1, Q2 and 1 upon R square. Okay. Now this was determined as much experimentally as it was established by conjecture. First of all by Newton, and later on by it was obtained by Cavendish, and it was also obtained by Coulomb in this case. But next I am going to tell you how the secular values are there and how this will happen definitely, that Winner's square relationship is a must in such situations that will exist. So the Coulomb's law has been derived as F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Well, here I would like to tell you that the variables, I have Q1, I have Q2 and I have R. Okay, and of course as a result thereof F is also a variable, isn't it? So what is the status of the constant? So 1 upon 4 pi, 1 upon 4 pi epsilon naught, it does not depend on Q1, does not depend upon Q2, does not depend upon R, and does not depend upon the measured force. What does it depend on? It is independent of. So, like I said before also, I am emphasizing again, I told you in the case of Newton's law of gravitation also, where the capital G did not depend upon M1, did not depend upon M2, and did not depend upon R. But capital G there also was a function of the system, function of the system. The system, the defined system, Okay, in Arabic, this article is known as al. System means nizam, so this becomes al-nizam. Nizam hada, this nizam. Okay, this system. Whatever system I have defined. I have taken up a system, isolated system in there. Two charges separated by distance r. The r can change, q1 can change, q2 can change. Okay, and the force can be measured, and that will also change. So 1 upon 4 pi epsilon naught in vacuum will not depend upon the values of q1, q2 and r, etc. So defined variables cannot define you the constant of the system. Okay. Now here I have drawn something. Okay. What is this something? Looks like a circle, but actually this is a section of the ball. The ball is very small. Okay. I should have taken a football or a volleyball or anything. So now if we take a section, this circular thing, this point is the center of the sphere. What I said? The center of the circle and the center of the sphere, if it is cut, then it turns out to be one and the same. The radius we take as r. Do you know what is 4 by 3 pi r cube? 4 by 3 pi r cube is the volume of the sphere. Volume of the sphere. What is the surface area? 4 pi r square. And this is one of the most beautiful things in the nature. For a given volume, the minimum, the shape with the minimum volume will be a sphere. The shape with the minimum surface will be a sphere. Like the shape with the minimum circumference is a circle. So these are the beauties of these geometrical constructs. Okay, you must always bear in mind. Now, what I do is, I am trying to tell you why the effect that we have here is this F was proportional to 1 upon r square. So look here. Let's see, in the green lines that are going there, I have shown them something exiting out. Okay. Anything exiting out is called flux out. Flux out. Out of the volume, out of the surface, piercing the surface here, there, everywhere. I've just taken a very small number of lines. Okay. Equivalently, I can say that there is, with the red signs over here, I am showing that something is entering into the system along these straight lines, which are equally, I'll say, spaced, okay, furcated, the diversion of the lines is almost equal. I have a bad drawing, so maybe there are something, this angle may appear to be less than this, but all angles will be equally there. Okay. Now, this is exactly what happens if you have a mass over here, okay, and then lines of field, they come towards that mass. If there you have a positive charge, then I'll tell you, the lines of field will go like this, equally diverted from each other. Okay. So all directions coming out of the spherical body, they are equally preferred. Equally preferred. Now it doesn't matter whether we have a mass over here, or whether we have a charge over here, or whether we have a source of light or electromagnetic radiations which is placed over here, and we have a vast space around it, and that means we can put something over here, or which emits out or absorbs something from all possible directions. Okay. So when all directions are equally preferred, there is no equitable distribution. Okay. There is nothing like my brother, my cousin, my village, Vasi, Pravasi, nothing like that. All are equally preferred. Vasudhaiva Kutumbakam. Okay, is what we say in Sanskrit, one of our revered languages. So when all things are equally preferred, then there is a something over here, something fluxing out or something fluxing in, and this is the center. Then what is the effect on that surface? What is the effect on the surface of that ball? Okay, so if this is the surface of the ball and I just take a small area of the ball, okay, here, then something will come out, and that will show the effect. And please visualize, come over here where I have reduced the number of lines to 4 only. Okay, look here. One line is going like this, another line is going like this. That is the neighboring line. There is an arc over here, arc 1, and there is an arc over here. The angle, of course, is 90 degrees over here, but I say that what is an angle? Angle is arc upon radius. Angle is arc upon radius in a circular system like that, and it's positive if we go anti-clockwise and it's negative if we go clockwise. Okay, so you can see that for the same area, 1/4 of a spherical area of a sphere, that is 4 pi r square divided by 4 in the pi r square area. Here the effect will be more, and here the effect will be, because of the spreading, the effect will become smaller. So the effect will be equal to something divided by something happening divided by the total area of the sphere. And that total area of the sphere, like here I told you, is 4 pi r square. It's very simple, friends. Effect is equal to something upon 4 pi r square. I take 4 pi, something upon 4 pi separately into 1 upon r square, and this something is a constant. We take it as a constant. We assign it a constant value. And 4 is also a constant. Pi. What is pi? What is pi? You'll say 3.14. No. Pi is in a circle. Pi is called the circumference divided by the diameter. Okay, that is the definition of pi. 3.14 is just a value. So you must understand what it is. It's essential, it's very important. If you understand that, what is pi? Pi is the circumference divided by the diameter. 2 pi r divided by r. Okay. By 2. Circumference is 2 pi r divided by the diameter, which is 2r, will give you pi. Okay. So pi. This is a constant. So this whole thing becomes a constant. So this effect becomes a constant into 1 upon r square. Now, in a systems approach, I can say that this effect is proportional to this variable 1 upon r square. This gives us what is known as the, in my this thing, that there has to be in a secular situation an inverse square law, which of course very diligently was determined by and established by Mr. Coulomb, as also by the Cavendish experiment. Of course, there was Newton who speculated, who thought that this kind of a thing will occur. Friends, this drawing simply shows that because of the charge over here or because of the mass over here, there are some lines which are coming, which are diverging when flux out is there and converging when there is a flux in. These lines, as I told you, in the case of Newton's law of gravitation, they are field lines. So the next thing I will talk to you about in the coming lecture is as to what is field and how it is related, but I would like to suggest to you that take a couple of protons, put them at any distance you like, okay? They have a charge which is equal to plus E, 1.6 into 10 to the power of minus 19 coulombs, okay? And distance between them, you take any distance, doesn't matter. And they have a mass also. That mass is also given, or Google it, okay? Apply Newton's law of gravitation, find out the force. What will be the force of attraction between these two protons at such and such distance? Then calculate as to what will be the force between these two protons, not because of the gravitation but because of electrostatic Coulomb's repulsion. Okay? Just see as to what is the electrostatic force and divide it by the gravitational force, and you will be astonished to see that the Coulomb force is much higher as compared to the gravitational force. The same thing you can repeat with an electron and a proton and two electrons, etc., and you find very interesting data you can find all by yourself. I will not do that. You will do it for yourself. So, I hope you have enjoyed. I have given you something which is normally not available in the text and in other books. This is how I just take something. In Hindi, I will call it kuch. Kuch. Anything, damn it. But there is a flux out or there is a flux in. In both cases, this secular relationship where all directions are equally preferred gives us what? Inverse square relations. So long. See you soon.